In the last lecture, I talked a bit about the specific activity. I said enzymes are so specific, sometimes it can be absolutely specific and sometimes it can be group specific. Think I draw some images. Let me go back. Yeah, this one. If you look into this image, so these are absolutely specific. Yeah. So they can, if you take two chiral compounds, they can recognize only one form of the enantiomer. Yeah? So sometimes enzymes can be so specific to the molecular structure, and sometimes they can be specific to the group. In this case, this particular group, and so it can recognize both ethanol and methanol. So this structure. Yeah? So if we take only this part, so enzymes can recognize some particular functional group. So this type of enzyme molecules are called group specific. So we need to know such information or this type of properties of enzyme for few specific reasons. So we will come back to that when we are going to derive this mechanism and kinetics. Probably I will try to finish this in this particular lecture. Yeah? I'll try to derive this whole expression. So there is a reason. So your enzyme will have some catalytic property, and it can act only on particular reactant, and it can give only some particular product. So enzyme have these beautiful properties. So we call them as a specificity. And why is that? Why enzyme needs to be so specific? And there are few theoretical hypotheses for that. So why enzymes are specific? Enzymes are specific. Or if you want, why enzyme possess such beautiful molecular recognition capability? Either it can recognize only one form of your enantiomer, or it can recognize only some type of molecules that possess some specific functional groups. So that's what we are going to study in this lecture. So I already said enzymes are molecules. They have definitely have some molecular structure, which means atoms are arranged in a pattern so that it to give its unique molecular structure. Yeah? So I will upload the PowerPoint for the previous lecture and for this lecture. So there I pasted few of the images of the enzymes. You can go and have a look how enzymes look at molecular level. Yeah? So why enzymes are so specific? So we are going to see few theoretical hypotheses to explain why enzymes are so specific and why it targets only some particular molecules. So you just a reminder, like if you have so many reactants here, enzymes can recognize only one type of your reactant and can produce only one type of product. So it won't produce many products here. Yeah? So it will produce only specifically one product. So enzyme not only have the capability to recognize a specific type of a reactant, but it also have the capability to break that specific type of reactant and will always produce only one type of product. So that's why enzymes in industries, they like to use enzymes, like so they don't have to spend a lot of money. Imagine if your enzymes are producing too many different type of molecules, it breaks some compound A and breaks into 3 or 4 different type of compounds, then you have to spend a loads of money to separate these different type of compounds that you observe in the product stream. So that's why enzymes are good to use in industries. Yeah? And let's go on to few of the hypotheses that can explain why enzymes should be so specific. So let me go to my notes. So first one I'm going to see is it's a hypothesis proposed by Oxton in 1948. So what he said, I'm going to explain. Probably I can use some different colors. Say you have a tetrahedral carbon structure. Let's see. So I said to you, enzymes are like absolutely specific. So this is the theory proposed by Ogston to explain this particular property of enzyme, why enzymes are so absolutely specific. Imagine you have a structure like this. So just assume this is your reactant molecule. And just assume we have an enzyme that have a, say, some structure like that. And it assume it has say this is your enzyme, and assume it has 3 different points. Yeah, so point 1 here, point 2 here, and then point 3 here. So this is your third point, and this is your point 1, and this is your point 2. So what he said is like, so if you have a reactant molecule like this, your enzyme, which is shown here, just call this is your enzyme, it should have at least 3 different reaction sites, or he call it as active sites. So what he said is like, say this molecule, this atom here in your enzyme, go and stick here, and this group, it go and stick in the location 3, and this one it go and stick in the location 2. And so you need at least 3 active sites on an enzyme molecule so to recognize your reactant. So this is one of his model. And just imagine, so this is say this is your L form, so just you imagine the D form, the other side, the mirror image of the same molecule. I'm going to draw in the next page. So just imagine this is your reactant molecule now. And now you take the same enzyme. Yeah? We'll try to draw like similar structure. Just assume for the moment this is your enzyme, and just assume you have the same 3 different spots here. This is your active site 1, active site 2, and active site 3. So what he proposed is like, if enzyme can particularly have some, just imagine these are your reaction sites that can recognize only this type of functional group. So and this is your reaction site that can recognize only this type of functional group, and this is your reaction site that can recognize only, this type of your atom in your enzyme molecule. Yeah, so in your reactant molecule. So clearly you cannot take this molecule and place it on this type of enzyme, because this compound or this particular atom, no way it's going to react with site 3, and similarly this particular group of atoms, no way it's going to react with site 2. But this one can be recognized. Yeah, this one can be recognized by site 1. So but since 2 of your reactive sites cannot be recognized by enzyme, so enzyme will ignore this molecule. Say imagine you take your some bioreactor, and then you load with your enzyme, you load with your reactants, like one form of your reactant, and you load also another reactant in the same reactor, and then you add your enzymes inside. Say these are your enzymes. So this is your enzyme, D form, say L form, so enzyme can recognize only this compound. Yeah, so they go together. So this one, no. So this is the hypothesis proposed by Oxton. So instead of 1, 2, 3, he called it as ABC. ABC, and what his hypothesis says, or what he proposed, is you need at least 3 active sites in your enzyme, and for your reactants to be recognized from a solution. Yeah, so if you don't have, so his hypothesis is like, whenever enzyme recognize a reactant, which mean at least 3 active sites are involved in this molecular recognition process. So it's not one reactive sites, it's not 2 reactive sites. So he said, if you think your enzyme can recognize a particular reactant, at least 3 reactive sites must be involved, so that your enzymes can recognize a particular reactant. Yeah, so this is his hypothesis. So if that's the case, then your enzyme can screen like this type of, let me change the color. Your enzyme can screen, so this type of, I don't know why I cannot see the color here. So your enzymes can effectively screen this material from this reactant. So that's the hypothesis. Yeah, so you need at least three specific sites in your enzyme molecules to recognize a specific type of your reactant. So, and that's how enzymes can be absolutely specific. If your enzymes are absolutely specific to a reactant, which means this enzyme can recognize 3 different sites from your reactant molecule. So that's one of the hypotheses we covered. And whenever I talk about active sites, so enzymes are really large molecules. Yeah, you have so many atoms connected. So it's enzymes are really large. Yeah, I cannot draw it here because you will have. Give me a second. Shalini. The pen. Oh my God.